To AP Statistics. This is Unit 1, Lesson 10, Exploring Density Curves. Today we're going to learn about the 68, 95, 99, 7 rule, and we're also going to be looking at the density curves. All right, so the first thing that we did is, let me bring it up again. All right, I had 3 different experiments that we did in class. So if you're at home, you can do this experiment for yourself if you want to get the experience. So the first thing we did is I had everybody roll a dice 3 times, and then they recorded what they rolled. Then they sent me the data, and I collected all 30 people in the class, so there was about 3 times 30, so about 90 pieces of data that I sent back to them. Second experiment, what we did is we tossed a penny. And they had to, I put a target about at the edge of their desk, and they had to try to get the penny on the target itself. Then they measured how far that they missed the target, and they did it 3 times, sent the data to me. I collected the data and sent the data back to them. And finally, the third experiment was to take their iPhone or their Samsung or whatever, any of their phones, and get their stopwatch to land exactly on 5 seconds. If they got 4.95 and it was a little bit under, then what they recorded was 4.95. If they got 5.04, then they recorded 5.04. Whatever they got, whatever their stopwatch was reading, that's what they recorded on their survey and sent it back. So the next thing that they were supposed to do is they were supposed to predict what it would look like. And this is a potential prediction showing 1, 2, 3, 4, 5, 6 are all of the possibilities for rolling a dice. And you can see that the prediction is pretty well close to about even. And the actual, this is the in theory, where if it was done many times, let's say, over a period of 1,000 different rolls, this is about what would get. You see the mean is going to be equal to the median, and the probability of each one is equal to 1/6. So if you see that the 1/6 high and then 6 long, 1/6 times 6 is equal to 1. So the area of this density curve itself is equal to 1. This is called a uniform distribution because it is straight across and everything has the same probability for each value. Okay, the second experiment, this is just whatever prediction you thought it was going to be, but the actual was this. And this is where the mean is greater than the median because it's skewed to the right, which I'll talk about in just a second. The reason that it was like this is because if you think about it, I cannot go any lower than 0. That's the lowest I can be because I'm trying to, literally I have this desk here and I have a spot here and I'm trying to flip my penny right on that spot. So if I flip it exactly on that spot, then that's going to be my 0. But if I go over, I had some people go over and hit off their desk and they basically, I drew a vertical line and had them do what the distance was. But they could go really far. And in theory, they could be infinitely away from that spot. So in theory, they could be that far away. But most people are going to be probably somewhere in this circle-ish area. Those are going to be where most people's are, which is right about here. That's where most people got. So this is skewed to the right because you really can't go far to the left. Most people were right around 20 centimeters, but you can go far to the right. And so a couple people missed it way on target, which is causing it to be skewed to the right. And the reason the mean here is greater than the median is because in order to calculate mean, I add up all the numbers. So if this was the values, I would add up all these numbers, 1 plus 3 plus 5 divided by 3, and that would get my mean. But pretend like I had one of the values at 50. 1 plus 3 plus 50 divided by 3 would definitely way increase my mean. But if I had 1, 3, and 50, or 5, 3 would be my median. But if I had 1, 3, and 50, 3 would still be my median. So my median only changes if I take a value from one side of the median and change it to the other, like this. If I have 1, 3, and 50, we already determined that 3 is my median. But let's change this to 10 now. So now 1 was on the left side of the median, but I noticed I had a mistake, and now and it's not 1, it's actually 10. So yes, my median did change, but by just 1 position and not drastically the way it would for mean. So for the next one, we determined that this one, you can be whatever you want it to be for prediction, but this one turned out to be approximately symmetric and approximately normal, where the mean and median were the same and it was a bell-shaped curve. All right, so the first step we're going to do on this next one, it asks you to label mean and standard deviation. That's my mean. Standard deviation is 0.18, so you add, this was just, oh, sorry, it's not on this one. This one was just my label of what I did, but this one here is my, there we go. There's my mean, and I add 0.18 to each one, add another 0.18, and 0.18 is what my standard deviation is for each one of these. If I added up all my data, you'll see on this one, basically what I did is I added up all my data, and on our data, we had about 90 pieces of data, and we had about, from 1 to standard deviations, what I did is we added them all up. We went over here and we said, okay, let's count them all up, and we counted our values. And this is from here to here, from 2 standard deviations. I got about, I think about 85. I got about 85 out of 90. And so 85 out of 90 is about 94%, close to 95%. So I got 85 out of 90 on my data. And then so how many is further than that? Then that's about 5%. How many is greater than 1 standard deviation? So I counted up my data. Greater than 1 standard deviation, that way would be what that would be. And then I counted up my data, and we got about 14 out of the 90, which is about 16%. And what percentage is between -1 and +2? And we also, that's -1 is this one here, to +2 is this one here, and we got about 81.5%. The way we got this data is that the actual raw data that I gave them, like they knew what their values were. They knew what everybody's values were exactly, and so we just counted what their values were in between what this was. I also added here, and I asked everybody to write this down on the side, and I did 1 standard deviation, 2 standard deviations, and 3 standard deviations of the mean, and this is what we ended up getting. We ended up getting about, as I said, the first one was, we did out of 90, we had about 63 dots out of 90 within 1 standard deviation of the mean. So basically 1 standard deviation of the mean was between 482 and 518. So what we did is we looked at our chart and we counted any dots that were between 482 and 518. So 4.82 to 518, and we counted all those, and I got 63, and 63 divided by 90 is, let's do that real quick, is about 70%. Then I told you this one, we did the same thing for 85, and that one I did from 4.64 to 5.36, and from 4.64 to 5.36, we got 85 out of 90, which 85 divided by 90 is equal to about 94%. And then 3 standard deviations of the mean, we got about 89 out of 90. And so 89 divided by 90 is about 99%. So what we're going to see here is that if you read into your chapter 5, you're going to see there's a rule called the 68, 95, 99, 7 rule. And I want you to label on here 1, 2, 3. And what that rule means is that if it's a normal model, like this one seems to be, if it's a normal model, that my data, 68% of my data about will lie within 1 standard deviation of the mean, which means between 482 and 518. And indeed, we got really close to 68%. We got 70%. So it's really close. And it doesn't have to be exact because remember we are doing trends of data and it doesn't have to be exact. For 2 standard deviations, what it's saying between 464 and 536, so all of this here, all of those values, about 95% of my people would have values between those values, and we did get about 94%. And I'm just talking about the stopwatch one because it was the only one that looked fairly normal. The other ones were not normal models, so they would not be able to do what I'm doing here. And finally, the last one is 99.7, And we got 99%, so we were really close. And we found that 99.7% would basically be under almost the entire curve, between 446 and 554. So the learning targets here are, number one, seeing a density curve. The total area is going to be 1 under a density curve, and it's uniform distribution. Learning target 2 is that it's symmetric. Of course, remember, the mean is equal to the median on symmetric graphs. When it's skewed to the right, you're going to see that the mean, the skewness, the outliers is actually pulling this. If this is the mean, then, or excuse me, if this is the median, then maybe this is the mean, that the outlier is pulling it out. And for this one here, it's the opposite. If this is the mean, the outlier pulled the mean out, remember, then this would be my median, somewhere around there. Okay. Learning target 3, the empirical rule, which is also called the 68, 95, and 99.7 rule, which 100% of the time you can call it the 68, 95, 99.7 rule. It's labeled like this. The N here, you're always going to, for title, label, tick, 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 for your graphs, this is your title. This means it's a normal model. That's your mean is going to go there, and that's your standard deviation is going to go there. The reason I'm using mu and sigma is because it's a model. The normal model is a model, and it's going to be used for purposes in trying to see if our sample is valid. And you can see within 1 standard deviation of the mean, it's 68%. Within 2 standard deviations of the mean, let's put SD. 2 standard deviations below and 2 standard deviations above, it's 95%. And 3 standard deviations below and 3 standard deviations above, it is 99.7%. Okay, let's go ahead and check for understanding. What height must the density curve have? Justify the answer. Well, we know that the height must have a curve of 1/10 because there's the difference here is 10. And area is equal to 1. About what percent of the guests cut their yarn longer than 48 inches? Well, if you take the base minus the 48 inches, because that's where we were, we end up getting 2. And then we have to multiply it by the height, which is 110, and we get 0.2. And then please go ahead and make sure you put the context. Calculate and interpret the 25th percentile. So the 25th percentile, that means the area is equal to 25%. Well, we know that 25% times times 10, because that's how wide my bracket is going to be 2.5. And then I say, well, I'm going to be part of the 25th percentile. So I'm starting with 40 because that's my lowest spot. And then I'm adding 2.5 because I know that 25% is going to be 2.5 up. So I know that that's going to be here. And that there is going to be about 25%. Oh, that's 50. So sorry, it's going to be more like here. And you can see clearly that is actually 25% of it, because if we split it into 4 parts, 1, 2, 3, 4, 25%. For sketching the normal model, if I ask you for the normal model, that remember here the mean tells you it's 44 and the standard deviation is 4. And so this is 44, and then you're just going to go up by 4. And remember, that's the mean and that's the standard deviation, and N means that's a normal model. What percent of women who are 8 months pregnant have a waist circumference less than 40? Well, less than 40 inches, you can go ahead and see for, by labeling the normal model, you can see that if this is 68%, then this is 34, and this is 34. If this is 95%, and we do some math, and we say, okay, 95 minus 68 is going to be 27. And so that means that this area and this area together equal 27, but they're symmetric, so that means this little part's 13.5, and this little part's 13.5. So then we can do the same process here. This here is 99.7. So 99.7 minus 95 is equal to 4.7. So this little here and this little here is equal to 4.7. So divided by 2, because they're symmetric, that's going to be 2.35, and that's going to be 2.35. And then now remember 99.7 is within 3 standard deviations, which let me just kind of use my highlighter from here, that's 99.7. But remember, on the outside, what else do we have? So the outside here, that is going to be the rest of it. So if 997 is the blue part that I shaded, then the rest of it is going to be 0.3, and divided by 2 is 0.15, 0.15. So all I did was, to get this answer, is I added up all of these because it asked for less than 40 inches, and 40 inches is right here. So I'm looking for all of this area right here. And for this one, is greater than 52 inches may indicate amniotic fluid. What percent of women who are 8 months pregnant may have excess of amniotic fluid? So 52 or more is 52 or more. So I'm looking for this area right here. So you can add these two values together, which you do get 2.5%. Or the way the publisher showed it is I take 100 minus 95. The reason it did that is because it noticed that, hey, this is already at 2 standard deviations. Remember I told you 2 standard deviations, it's hard to see with all my writing on here, is 95%. So the outside is going to be 2.5% on each side. So if 95% in the middle, I'm going to have 2.5 here and 2.5 here. And so that's the other way to get it. All right, I hope you understand this lesson, and we're going to be doing more about normal models on the next lesson. Thank you.